In this video, I'm going to talk about solving linear programming problems using the graphical method. Using the graphical method to solve a linear programming problem has one major limitation, namely that the number of variables that we can have must be 2. This is because if there are 3 or more variables, then we need to draw it in a 3-dimensional space or higher, which is not something that we can easily do. When we start solving a linear programming problem using the graphical method, we need to start with the constraints, but not the objective function. This is just like we need to first know our boundaries before we can find out how to maximize our own potential. To graph the constraints, we need to know how to graph a single inequality. Let's begin by graphing this inequality. To do that, we first turn it into an equation. This equation is representing a straight line, so we should try to find out the intercepts. To find out the x-intercept, we treat y disappeared because we need to substitute y to be 0. Then we have x equals to 9, which means that the x-intercept is 9. To find out the y-intercept, we cover x, which means substituting 0 into x. Then we get y equal to 9. And we should try to connect these two dots to get a straight line. Now we get the straight line, but we still have to find out the inequality. An inequality represents one side of the straight line. We also call it a half plane, either this lower half plane or the upper half plane. How do we determine which half plane is the correct one? One quick way is to substitute any point on this plane that is not on the straight line into the inequality and see if the inequality is satisfied or not. Usually, the origin 0, 0 is a good choice. 0 plus 0 greater than or equal to 9 is clearly a false statement. In other words, 0, 0 is on the wrong side of this straight line. So we should not use this half plane, but this half plane. Next, let's try to graph this inequality. We first turn it into an equation, and this once again represents a straight line. So we cover this term so that we have negative 3x equals to 20, which means x is equal to 20 over negative 3, which is around negative 6.6. So we graph it somewhere here. And to find out the y-intercept, we cover the x term, which means 4y equals to 20. So we have y equals to 5. So we mark 5 somewhere here. And we should try to use a straight line to connect these two dots. Once again, we need to decide whether this side of the straight line or this side of the straight line should be taken. And we are again substituting 0, 0, and we have 0 plus 0 is less than or equal to 20. This is clearly correct. So 0, 0 is on the correct side of the straight line. So we should take this half plane instead of this. Finally, to graph this inequality, we once again turn it into an equation. The x-intercept is given by 60 over 7 after we cover 4y. 60 over 7 is around 8 point something, so we mark it somewhere here. 60 over 7. To find out the y-intercept, we cover the x term, so we get y equals to 60 divided by 4, which is 15. So we mark it somewhere here. And we need to connect these two dots. And once again, if we plug in 0 and 0 into x and y, we found that this inequality fails. And so 0, 0 is on the wrong side of the inequality. So we should pick this side of the half plane. We are almost done, except that we still need to take care of x greater than or equal 0 and y greater than or equal 0. These two inequalities restrict ourselves to the first quadrant. Now, combining all 5 inequalities, we found that the overlapping region is this portion of the xy plane. As you can see, this portion satisfies the yellow inequality, the green inequality, the blue inequality, as well as it is within the first quadrant. We should shade it to indicate that this is our region of constraints. Next, we are ready to study the objective function. It is ideal to keep track of all the equations that got us these strict lines. To tackle the objective function, all we need to do is to plug in these vertices of our region of constraints into the objective function and find the maximum or minimum values among them. Well, it sounds a little bit complicated. So, first, let's try to notice that the region of constraint has vertices that include this, and this, right? The coordinate of this vertex is easy because it is on the x-axis. So the coordinate should be 9, 0. How about this particular vertex? It is the intersection of the green line and the yellow line. So we should take the yellow line and the green line and put them together to solve the system of linear equations. If we multiply the first equation by 4, we have 4x plus 4y is equal to 36. After subtraction, 4y cancel, and so we are left with 3x is equal to 24, or x is equal to 8. Substituting this into the first equation, we have y is equal to 1. So the coordinate of this vertex is 8, 1, where 8 is the x value and 1 is the y value. How about this vertex? This is the intersection between the blue line and the yellow line. Therefore, we should take negative 3x plus 4y equals 20 and 7x plus 4y equals to 60 and solve them together. This time, we can just simply subtract them and we will have 10x is equal to 40. So x is equal to 4. Substituting this into the first equation, we have negative 12 here. Adding to the other side, we have 4y is equal to 32, or y is equal to 8. Therefore, the coordinate of this vertex is 4, 8. Technically, there's another vertex that you don't see, namely infinite and infinite for both x and y. But because we are minimizing this particular objective function, if x and y are infinite, then clearly that value is huge, so we should ignore that particular vertex. After we have obtained all the vertices of the region of constraints, we should plug in the vertices into the objective function one by one and calculate the c value. So, at the vertex 9, 0, we will have c is equal to 5 times of 9 plus 3 times of 0, which is 45. At the other vertex 8, 1, the c value would be 5 times of 8 plus 3 times of 1, which is 43. At this vertex 4, 8, the C value would be 5 times 4 plus 3 times of 8, and that is 44. Out of these three values, we found that 43 is the smallest. Because we need to minimize the value of C in this problem, therefore, we have obtained that the minimum value of C is 43, occurring at x, y is equal to 8, 1. This solves our linear programming problem. Here is the summary of using the graphical method to solve a linear programming problem. There are two steps. First, we try to graph the region of constraints. Second, we will plug in the vertices of the region of constraints into the objective function. When graphing the constraints, we try to graph the inequalities one by one, and we first graph the straight lines using the x-intercepts and y-intercepts, and then we will try to find out which half plane is correct by plugging in, usually 0, 0, into the inequality. Then we will try to find the overlapping region of all the inequalities and shade it. When we try to plug in the vertices of the region of constraints, we first try to find out the coordinates. Sometimes we will need to solve a system of linear equations so that we can try to find the vertex. After all the vertices are found, we will plug the vertices into the objective function to find the largest or the smallest value. Thank you very much for watching. If you like this video, please subscribe to our channel and we will learn more fun math together. Thank you.